us and have fun. All right, so if you don't have any question, let's proceed. And let me just turn this truck on also. That's better. So last time we discussed about the case that sometimes you do have a system that there are so many motion is happening. One is moving inside. It's like you have a can with lots of marble in it, and you are shaking. The marble is inside that can is moving. Your can itself is moving. Maybe there are other things moving. So it's very complex. You have a system that's very complex. And you would like to use auxiliary coordinate system to describe the motion. So you can say that this is a main reference frame, capital XYZ. And this is one of your object, maybe can or car. And you attach, and this is, you can say, point O. And this is like you look at the whole car as one object. And then you attach one auxiliary reference frame here, a small XYZ. And then you do have a particle which is moving respect to this auxiliary coordinate system. And the distance of that rho is changing. So just forget about this one. And just you are, from the car, you are watching something inside, and that is moving respect to the car, or respect to the can. The can itself from outside is moving. So this is a main reference frame. That's RO. And that is R to the point. So now you can say the positional object respect to main reference frame can be described as R is equal to RO plus rho respect to XYZ. And if I want velocity, velocity simply would be R dot O. What is the velocity of this car itself? Forget about object, and as if I don't care about object. Then you do have rho, which is a rho dot, which is the velocity of the object respect to the car. That's we call it VXYZ. But because the car is tumbling, if it is tumbling, and it is rotating, the car is maybe tumbling, then this auxiliary reference frame may be rotating as if the car is tumbling. Then you do have omega times rho XYZ. This is provided that this object itself with this attachment is tumbling. So it is rotating with some angular velocity omega. And if it is tumbling, this XYZ, which is attached to the car, is also rotate with the car. Rotate with the car. Therefore, rho, which is also inside the car, is also rotate with the car. So therefore, everything is like frozen, and that is moving. So you do have two component of velocity, three component. How is the car? What's the velocity with respect to XYZ? And if the car is tumbling, what is that? You can also go ahead and find acceleration respect to main reference frame as R double dot O plus, now you make a derivative of this one, that is would be acceleration respect to a small XYZ, but because the velocity is tumbling, it has two terms. So it has AXYZ plus omega times VXYZ. This would be omega dot respect to main reference frame times rho XYZ plus omega times the derivative of this one, and this has two terms, one respect to XYZ and also being tumbled. So now you have VXYZ plus omega times rho. And if you put them together, all of this there, you can see that acceleration to main reference frame becomes equal r double dot O plus AXYZ plus 2 omega times VXYZ plus omega dot times rho XYZ. All of this thing is vector, plus omega times omega times rho XYZ. And this term is called Coriolis acceleration. Acceleration, Coriolis acceleration. So, and that is what we, and this is a two equation, and you may have multi references. You have to go from the last one to the second one, from second one to the first one, and from first one to the main reference frame. But you implement this equation. You implement these two equations. And with that one, we solved one problem last time, which was actually my exam problem when I was a student like you, and which our famous professor, Professor Crandall, gave us that question in exam. So we said that you have a disk here, a disk, and you do have a blade which is attached to this disk, a blade which respect to the disk it has some angle theta. So at any, and the radius is this one is r, the length of this one is l, and this point is a p. And this is rotating with a constant, maybe we can say omega and omega dot maybe. This time we make it a little bit much more complex. But that time Professor Crandall gave us it goes with a constant velocity. So let's say with a constant omega. Constant. But phi itself is not constant, and phi keep on changing, and it goes like that. So we are interested to know what is the velocity at any time. What is the velocity of this one respect to some main reference frame, respect to main reference frame, capital XY, Z. And of course, this is moving in a page of the blackboard, so it doesn't come out of the page. So you can say, no problem. This looks complex, but it's not really complex. And you can say, OK, I like to use the concept of auxiliary reference frame. And I would like to attach one auxiliary reference frame right here, like XY, and Z is coming out of the page. I can attach here some auxiliary. And as you see, without even having this arm, my auxiliary reference frame is being twisted. My auxiliary reference frame twisted. And if you freeze this one, then you can see your arm is moving in respect to XY, a small XY. So we are interested to see what is the velocity of point P. So you can say, no problem. If I use the concept of auxiliary, so we can say that, and this is at this point is a tangent to this direction. So you can say velocity respect to main reference frame, velocity of point P respect to main reference frame is equal to, and this point we can call it O, r dot O, plus velocity of the P respect to a small xyz, plus omega, that my auxiliary reference frame is being tumbled, times rho xyz. So r dot O is basically velocity of this point. Forget about this section, as if this section does not exist. This section doesn't exist. And as you see, the velocity of point O here is simply r omega, and it is tangent to the circumference, and it is in the direction of a small I. small j. You can say it's in this direction. So you can say r dot o is equal to r omega, and the direction of that one is in direction of small j. If you would like to say is in this direction. So that's r dot o, and that's equal r omega, and that's velocity. That's one of the vector. Now you just look at this one. You look at this x, y, as if this doesn't exist, and this arm with angle phi is moving inside that a small xy. You can say no problem, that's also r omega. But omega this time is r phi dot, r phi dot. That's a cylindrical coordinate system, and the r in this case is L phi dot, and that velocity is in this direction, normal to this, normal to the arm. That is another vector. So velocity respect to xyz of point P respect to this xyz is equal to L phi dot. And if you know the phi as a function of time, how the phi is changing as a function of time, you have Excel sheet, you should be able to say what's a phi dot. And the direction of that one is in this direction. And let's call that direction E phi. E phi. So you do have one vector in this direction, one vector in this direction, and finally you have omega times rho xyz, and that is your auxiliary reference frame is now being twisted, and the one that is responsible for twisting of auxiliary reference frame is this omega. That is one it is twisting. So you do have another term omega times rho xyz, and that becomes equal to omega, and you use your right hand and is coming in the direction of capital K, normal to the blackboard, and times rho xyz, and is L ER. We can say this is ER, L ER. And K times ER is equal E phi. So that is L omega E phi. So now you put them together, and you do have the final velocity of point P, which is 3 vectors. So velocity of point P respect to main reference frame is equal to r dot o. R omega is in this direction, j, a small j, and that j is keep on changing, but at any instance is a small j. So it's r omega, a small j. Then you do have this term and this term, they both are E phi, so I can put them together, and that would be L theta dot plus phi dot plus omega, phi dot plus omega E phi. So this point has velocity here, the point P. It has one velocity is in this direction, and it has one velocity in the, and this is a phi, and it has one velocity is in this direction, which is normal to this one, or you can say that this is basically parallel to that one. The total velocity would be parallelogram. It would be in this direction. So you do have a total velocity that you can find is a summation of 2 vectors. And so you do have one vector here, which you can say this is one vector and this one vector. And in order to make that summation, you can just go ahead and this vector is normal to here. That is basically your this vector. And this angle is also this plus this is 90 degrees, This plus this is also 90 degrees, so that must be also phi, I guess. So now, and this vector is r omega. This one is L omega plus phi dot. And then you can use a cosine rule and see how much is the total velocity, and you can also find the direction if you are interested. But this is perfectly fine to show is as in a form of vector. In a form of vector, if you would like to say how much is the total velocity, then that's not a problem. You can find the total. Now, if you are interested acceleration, of this point, then you have to go ahead and evaluate all of this term. So the first thing that you have to do, and that's my equation. So I have to evaluate r double dot O. So again, I forget about this one. If I forget about all of this thing, and r double dot O is acceleration of this point O. And because this is going like a cylindrical coordinate system, is r double dot minus r theta dot square er plus 2r dot theta dot plus r theta double dot e theta and so forth that we have. We have only one acceleration if you evaluate based on cylindrical coordinate system, and there is only one acceleration in this direction. That's r omega square. So your r double dot O is simply minus r omega square. And you can say that this direction, we put it a small I. We can say minus r omega square, a small I. That is a r double dot O. Now you just forget about this disk. You do have some arm, and this arm is rotating inside of this one. So the length of the arm is constant, so we do not have r double dot. We just have r phi dot square, and we don't have 2r dot phi dot, r phi dot double dot. Our cylindrical coordinate system was like that. R double dot minus r theta dot square er plus 2r dot theta dot plus r theta double dot e theta. We do not have this, we do not have this. So we have two terms for that axyz, and axyz is equal to acceleration point p respect to a small xyz is equal to minus L phi dot square, and the direction of that one is in this direction, which you can call it ER, is in this direction. So that is ER, which basically your ER is here, and your E phi was here, ER and E phi. And that is in the direction of ER, plus 2r dot theta plus r theta double dot, which becomes L phi double dot. And the direction of that one is E phi, normal to that one. That's E phi direction. So you do have two unit vector, ER and E phi, and that is the two things that you have. Now you do have 2 omega times vxyz, and that is your Coriolis acceleration. So even something is going with a constant velocity, if it's being twisted, then you do have acceleration. So that's a 2 omega times vxyz. That's 2 omega vxyz is equal to the one that is rotating auxiliary reference frame is my omega k, normal to the blackboard. Use your thumb. Thumb is coming out of the page. And vxyz, we calculated from previous one, is L phi dot E phi. L phi dot E phi. And this becomes L omega phi dot And k times E phi, k is here times E phi, that becomes minus ER. K is here, E phi is here, k times E phi becomes minus ER. So that is, and you put negative in the front of it. Use your right hand rule and say product, a cross product of two vectors.
This should be 2.
We had 2? Yes, we put a 2. And you put 2 minus. Let me just write here a little bit better. Minus 2 omega L phi dot, and the direction was negative ER. K times E phi. K times E phi is negative ER. So that takes care of that one. Then we have omega dot, but thanks God for this case, my auxiliary reference frame is not accelerating. The angle of that one, it goes with the constant angular velocity and is rotating with constant angular velocity, is not changing. And then I have omega, so therefore the next term is 0. Omega dot times rho xyz is 0. Omega dot times rho xyz is 0, because my auxiliary never accelerate. Then I have the last term, omega times rho xyz. The last term, omega times rho xyz, and that's omega k times omega k, and rho xyz is LER. So first you multiply this one, k times ER. Again, k times ER is E phi. So this becomes L omega E phi. And k times E phi is minus ER. So this becomes minus L omega square ER. So you add them up, all of this thing is a vector, and then you do have acceleration of point P. Any question on this problem? So you simply add all of this vector, and if you put them together, that would be acceleration of point P, and all of those vectors, you now have to know which direction they are, and you add them up those vectors. Any questions? Any question? Yes?
On a homework assignment or a test, we have E phi, ER, small I, you know, where you specify, like, you want them all in terms of ER and E phi or I.
As long as you specify the vectors, that's all we care.
Okay.
As long as you specify each vector, like what I did in the previous one, whereas each vector direction here is, that's all it matters.
Okay.
We don't need to know more algebra. The rest is with the algebra. Okay. Now, yes, go ahead.
I'm sorry, I have a similar question about the VP expressed in terms of capital X, Y, Z, right? And why is there a small j there? I think that's related to the small x, y, z quantity.
Well, what you are saying, let's say for velocity. Velocity we had this vector, right? And this vector. So if I ask with respect to capital X, Y, Z, this is it. This is respect to capital X, Y, Z. These two vectors, okay? Now, if you would like to represent this one, respect to this coordinate system, you have to say what is my small j at any time means. And a small j at any time means, and this angle or mutual, this theta, a small j means sine theta minus sine theta capital I plus cosine theta capital J. So you can put for this a small I that I had somewhere, I do not know, for this or this small j that I had, you can say this small j, I can represent this one in terms of the capital I and capital J. So this is my this was my j that we said, and this is basically this vector here, and that's that, and this angle is also theta, this angle is also theta. So this would be, my j would be minus cosine theta capital I, no, minus sine theta capital I, cosine theta capital J. So now you have with respect to x, y, z. Same thing, this one, at any time, you would like to see what is that E phi. You can say no problem. The lines are mutually perpendicular. Again, this angle that happens to be in the direction, that would be different direction. That's this direction. So that's this direction. So that's E phi. And now you have to say what is this angle, and this one is a phi. And now you can say what is the total angle in the direction of I and j. So you can represent it. Coming back to your question, that was an excellent question that you asked. But once you have the vector, that's it. So it doesn't make any matter. Now, let's say that, coming back to your question, same problem. And this is my capital X, this is my capital Y, and this is my bar here, my arm here, and the length of this one, and this is a phi, and that's a point P. Suppose I do not want to use auxiliary coordinate system. I don't want to use an auxiliary coordinate system. I would like to use as it is. And I have x, y, z. And I would like to say what is my velocity of point P. And of course, as I said, you can always go back and see what is a small j means respect to capital Ij. So you simply decompose that vector in Ij. No problem. So you can say here is my problem. At any instance, this angle is a theta. At any instance, this angle is a phi. What is the coordinate of this point? So you can say the coordinate of that point, xp, is equal to r cosine theta I plus r cosine theta plus this angle plus L. What is that angle? Theta plus phi. Theta plus phi. Theta plus phi. And that is the whole thing is I in the x component. So you can say my vector r respect to main reference frame is equal r cosine theta plus this angle is also theta. So that would be L cosine theta plus phi, and that is I. You can say capital I so you don't get confused. If I want to know what is y component at any time, you can say that's not a problem. That's going to be r sine theta plus L sine theta plus phi. So r sine theta plus L sine theta plus phi, and that's capital J. So that's a position. That's a position. Now, if you are interested in velocity, you simply go ahead and make a derivative of this expression, and of course, your capital I and your capital J never change. Never change. The only thing is changing are this thing and this thing. So you can say velocity point P is equal to r theta dot, and of course we know that theta dot is equal to omega. We know that theta dot is omega. We know that. So that would be r theta dot sine theta negative cosine theta is equal to minus sine theta. The derivative of inside that respect to time, that becomes theta dot. Plus, and this becomes minus L theta dot plus phi dot sine theta plus phi. And this whole thing is I. And of course, you know theta dot is omega. You can substitute for this one omega. You can also substitute for this one omega. No auxiliary. No auxiliary. We just describe the position as it is, and we simply, of course, in certain problems it's much more difficult to describe the position. And if you just go ahead with the velocity that we just had here, you put a small j and you put the e phi respect to I and j, capital I and j, you should get the same thing. And for this one, that would be r theta dot cosine theta plus L theta dot plus phi dot cosine theta plus phi, and that's the capital J. And of course, this is omega and this is omega. That's what you have here, omega plus phi dot. And if you just go ahead, as I said, to go ahead and say, what is this E phi? And what is this a small j? And you decompose this one in terms of the capital I and capital J, you should get the same thing in the main reference frame. And that back to the question that he was asking. Same thing for the acceleration. Once you have this equation, you can simply go ahead and do one more time derivatives. One more time derivatives. And of course, you have to make sure, again, what is changing, what is not changing. And you do one more time derivative, and you have acceleration. Any question? So there is two different ways to do the problem. So let's give you another problem. And of course, once I have, as I said, this velocity here, you simply can go ahead and make one more time derivatives. And I just do for one of the term, so you can see how it is done. I just do this term, but you can do that one. So you can say acceleration of point P respect to main reference frame is equal. R is constant, omega is constant, no problem. This becomes minus R omega squared cosine theta. So that becomes theta dot, and theta dot, it multiplied by another theta dot, that becomes R omega squared. And that's what we had. You remember that we had acceleration in this direction, and that acceleration was R omega squared. And if you decompose it with this theta, then you get two components. You get two components in I and J. So for this one, you do have minus L. Again, omega is constant. That becomes phi double dot. And this is multiplied by sine theta plus phi. Then you do have minus L omega plus phi dot. Then the derivative of this one would be theta dot plus phi dot again, which is omega plus phi dot cosine theta plus phi. And that's the capital I. You can do the capital J yourself. And then again, this theta dot is omega. So you can describe the position, and there are so many ways to do that. Certain problem is much difficult, but this problem certainly was not that difficult to describe the position of the P respect to the capital XYZ as a function of the theta and phi, and you simply go ahead and make a derivatives. So let's give you another simple problem. Let's give you another simple problem. Let's say that we have some crankshaft here, and the length of this one is L. And then we do have, let's say that we do have 2L here, 2L here. And then we have a piston here, which is attached to here, a piston. And that piston is going on this direction, straight up and down on this direction. And this one, the angle is a theta, and it is rotating with angular velocity theta dot, and it has angular acceleration theta double dot. And we ask you what is the velocity of this piston, velocity at point P, and what's the acceleration of point P respect to main reference frame, which is capital X and Y. So you can say no problem, this piston is only moving in the X direction only, and the only thing that I have to describe, what is this distance as a function of the theta at any time. What is this distance, x? So you can say this distance is L cosine theta plus 2L cosine beta. So your x is equal to, x of the piston is L cosine theta plus 2L cosine beta. And of course, there is a relationship between beta and theta. What kind of rule do you use to find the relationship between beta and theta? What's the relationship? Sine. So you can say L over sine beta is equal to 2L over sine theta. So L over sine beta is equal to 2L over sine theta. Or you can say sine beta is equal to sine theta divided by 2. So you do have a relationship at any instance. What is that? And this is the position of that piston. So you simply go ahead and make a derivative of this expression, and velocity of the piston is equal to minus L theta dot sine theta minus 2L beta dot cos sine beta. And of course, your beta dot is beta dot cosine beta is equal to theta dot cosine theta divided by 2. So you do have a beta dot at any theta, and if you know the theta dot, you know the theta at any instance, you should be able to find both beta as well as beta dot. You put it back in this equation. So by this relationship, at any angle theta and at any angular velocity, you should be able to find both beta and theta beta dot. You put it back here, that's velocity in the direction of I, capital I. That's in the direction of capital I, or I. If you want acceleration, you have to do one more time derivative of this expression, and that becomes acceleration of point P is equal to minus L theta dot theta double dot sine theta minus L theta dot square cosine theta minus 2L beta double dot sine beta minus 2L beta dot square cosine beta, capital I. So you can describe the position and find what's the acceleration. Again, for any angle theta, if I give you angle theta, you should be able to say what angle beta here is. If I give you the theta dot, you should be able to say what's beta dot is. If I give you theta double dot, you should be able to say what's a beta double dot. So this is beta double dot cosine beta minus beta dot square sine beta is equal to theta dot square theta double dot cosine beta divided by 2 minus theta dot square sine theta divided by 2. So you should be able to find everything. All right. So you don't need auxiliary, but certain problem you have use auxiliary because otherwise it becomes such a complex problem. Let's solve another problem, then you understand, and let's use auxiliary coordinate system. All right. Let's say that you have a disk here. You have a disk here. And this is your main reference frame, capital Y, capital X, capital Z. And you have a slot. You do have one slot in this disk. You do have one slot. And then you do have a disk here, which you do have some bearing here. And that's like a floppy disk that you put. So you do have a disk. And this disk is rotating respect to its own axis with angular velocity omega 2 equal 5 radian per second. So think about it like a pocket. It has a pocket, and this disk is inside the pocket. And then you do have this whole system. It also rotates around this axis with 10 radian per second. And let's say that you do have some groove here inside that disk that's rotating, and you do have a piece of marble, and that piece of marble inside that groove, that piece of marble is coming down with a velocity of 20 feet per second and with acceleration of 10 feet per second square. So that's our problem. So we do have a small disk that has certain groove. Maybe it has some valve, and that valve opens and closes, and the valve moves down, whatever it is. And so the disk is rotating here, and this piece of marble is coming down. And we are interested at this instance that the disk is in a plane of the Y and Z. At this instant, that disk, a small disk, that we mean a small disk, is in the plane of the capital Y and Z, is in the plane of, you can do at any time when the small disk is anywhere, but at this instance when the configuration is like this, is in the plane of capital Y and capital Z. What is the velocity of what is the velocity and acceleration of this particle P respect to main reference frame, respect to XYZ. We have given you some distance here. From here to here is 5 feet. And the piece of marble to the shaft is 1 feet. So this distance at this instance is 1 feet. 1 feet. So what you have here, you have a disk and you have a groove, and this disk is rotating with a constant. It could be not constant, it could have acceleration too, but it's rotating with respect to itself 5 radian per second. And then the whole disk, which is like this one is in a pocket, the whole disk will go with the 10 radian per second around here. And we are interested to see what is the velocity of the P respect to the main reference frame. So this looks a little bit not that complicated, but you may say that I like to use auxiliary coordinate system. Auxiliary coordinate system. And your auxiliary coordinate system is attached to this disk. You can say my auxiliary reference frame is attached to this disk. Is not attached to the a small disk, is attached to the big disk. And you can think about it that this piece is simply moving, is rotating respect to this axis. So my disk is rotating respect to this axis, and my small xyz, it simply goes around. It goes around. Just you can think about it that the disk is going like that. Inside is rotating here, but the whole thing is going like. So now you can say, okay, no problem. We have velocity of particle P is equal to r dot O plus Vxyz plus omega times rho xyz. Very simple. So that's the equation for velocity, and you have to say what is that velocity at this instant. So you can say no problem. This is my disk, big disk, and this is my auxiliary reference frame, which is attached here, a small xyz attached here. Forget about a small disk. That is basically my coordinate, and inside this coordinate, this disk is rotating around a small x. So your r dot O is simply r dot O is simply like r omega or r theta dot, and the direction of that one is in the direction of negative I. So your r dot O is equal to minus 5 times 10, and the direction of it is capital I. Capital I. That your small xyz is here. At this instant, they are coincident. And just forget about this small disk. Just forget about a small disk. And you can say the velocity of this point, O, which is 5 feet from this distance, and this is going with a constant angular velocity of 10 radian per second. That's r omega. And the velocity is in the direction of negative I. It goes around the circle. And at this instance, that point is r theta dot. And r theta dot is 0. And r dot is 0. R theta dot is equal to r omega. So that's it. Now you have to say, OK, forget about the disk itself. This piece of marble is coming down. It's coming down, and it is also rotating. That looks like a cylindrical coordinate system or polar coordinate system to me. And this piece of marble is coming r dot er plus r theta dot e theta. So according to the cylindrical coordinate system, you can say is r dot er plus r theta dot e theta. So that's your equation for cylindrical coordinate system. If the arm is changing and is rotating, your r dot is simply, so velocity with respect to a small xyz. Let me see, where can I erase? Let me erase here. Well, let me write here. Vxyz somebody tells me at this instance, what is that? It's coming with a 20 feet per second down, so it's going to be minus 20 ER, but ER at this instance is the same as capital K. At this instance is the same as capital K. So it happens at this instance that this axis and that axis are coincident, not at any other time maybe. Well, actually at any other time, capital Z is always in the direction of capital K. So it's always this direction is here. This two direction changes, but this one is always in the direction. So at this instance, your ER is going to be in the direction of capital K. And your R theta dot, because this is rotating, then you do have in this direction is rotate in that direction, and that's R theta dot. R is 1 feet, and omega is 5, and the direction of that one at this instance is in the direction of negative J. So that would be minus 1, 5. The direction is capital J. So you do have two velocity. One velocity is coming here, one velocity goes here, and at this instant, it happens that that direction and this direction are in the direction of capital K and capital J. Of course, negative. Finally, this auxiliary reference frame, forget about the particle, this auxiliary reference frame is being twisted. It is attached to the big disk like this, and it's being twisted. So anything that is inside of that system is also get twisted, and that's omega times rho xyz. So that would be omega times rho xyz. And omega is equal, at this instance, is 10K. And rho xyz is also happens to be 1K. 1K. That's the same direction at this instance, 1K. And that's 0. So therefore, the velocity of the point P respect to main reference frame, velocity of point P respect to main reference frame is equal to minus 50I minus 20K minus 5J, and that's it at this instance. Okay, I put my direction is in the different direction, so my number is not exactly matching, but the number-wise is okay. But it's okay, I go with this direction. So I cannot follow my notes. Now, if I want acceleration of this object that is coming down, we said it's coming down with acceleration of 10 feet per second square, I guess we said. It's coming down with acceleration 10 feet per second square, and that's going with the constant omega again. Then again, you write your main equation. You write your main equation, and you can say acceleration of this point P respect to main reference frame is equal R double dot O, which is again, what is the acceleration of this point? Forget about disk and so forth. What's the acceleration of that one? Plus AXYZ plus 2 omega, which is my auxiliary reference frame is being twisted, times VXYZ, plus omega dot times rho XYZ, plus omega times rho XYZ. So any of this term has to be evaluated. Now you said, OK, R double dot O, it just forget about the disk. This is at the 5 feet, and it's going with the omega is in this direction. And we have two acceleration. One is tangential acceleration. one is normal acceleration. Our tangential acceleration is in this direction. Our normal acceleration is in this direction. This is r theta double dot and r theta dot square, and this is r theta double dot. And because my theta dot is constant, theta double dot would be 0. I have only one acceleration, and this r double dot O is equal to minus 5 feet, 10 square, and the direction of that one is capital J. Capital J, at this instance. Now you said, what is the acceleration of this particle that is coming down? So again, this is my object. It had 1 foot from here, and is coming down. Well, it is, again, it looks like a cylindrical coordinate system, and it's also being twisted. It's also being twisted with the omega equal to 5 radian per second. 5 radian per second. Let me write it down a little bit better. 5. So you can say, okay, again, according to cylindrical coordinate system, I have r double dot minus r theta dot square, er, plus 2r dot theta dot plus r theta double dot e theta. So I have my equation is in this form. R double dot minus r theta dot square, er, plus 2r dot theta dot plus r theta double dot e theta. That's your equation in the cylindrical coordinate or polar coordinate system. Your r double dot is coming with the acceleration of 10 feet per second square. We said that this acceleration, this particle is coming down with acceleration of 10 feet per second square. So your r double dot is equal to minus 10. Your r at this instance is equal to 1. And theta dot square is a 5 square. And your er at this instance, er at this instance is in the direction of capital K. So your er at this instance is in a capital K. Plus 2 r dot theta dot plus 2, your r dot is equal to 20 feet per second. It was coming down, 20 feet per second. That's what we said, that the velocity of the particle is 20 feet per second. So it's minus 20. And theta dot is equal to 5 plus r is equal to 1. And we do not have theta double dot. That's 0. That's 0. It's going to be the constant velocity. So your acceleration respect to its own coordinate system is equal to, this becomes minus 25 minus 35k. So this becomes minus 35k. And this becomes equal to 40 times 20 minus 200. And er at this instance is also, where is that one? E theta is in this direction. And that's negative I. So that's negative. So that's E theta. So that becomes 40 times 5. So that becomes 200. That basically becomes 200 I. 200J, I'm sorry. So your E theta at this instance, this is your X, this is your Y, and this is your Z, and this is capital Y, capital Z, capital X, and your E theta, which is this one, the direction of rotation, happens in the direction of capital J. So your velocity, your acceleration is equal to r double dot, which is minus 10, r theta dot square, 1, 5 square, and your er at this instance is in the capital K. Plus 2r dot is minus 20, theta dot is a 5 radian per second is rotating, And we do not have theta double dot. It's going with the constant angular velocity. So we don't have that. And your E theta at this instance is in this direction, which is capital minus capital I. So if you put them together, that becomes minus 25k plus minus 10, so that becomes minus 35k. And the other one becomes equal to 200j. 200j. Did I put j? J minus j. So that takes care of the small axyz that we have in our formulation. Now you do have other term again. Let me just write it down here. So that's your axyz. Then you do have 2 omega times vxyz. Vxyz. And now your auxiliary reference frame is being twisted with omega is equal to 10, and the direction of it is k. So that is 2 times 10k. And vxyz, which just solved it before, vxyz is equal minus 20k minus 5j. So we do have that one before. So minus 20k minus 5j. So that's a 2 omega, which my auxiliary reference frame is being twisted, times vxyz, and I have vxyz from previous calculation is minus 20k minus 5j. And if you just go ahead and multiply this one, k times k, forget about it, and k times j becomes equal to 100. And k times j is negative I, so that becomes 100i. So your 2 omega times vxyz, that becomes equal 100i. Well, we don't have this term. My auxiliary reference frame is not accelerating. So omega dot times rho xyz is 0. So I don't have that term. So let me erase this one. Or maybe I erase all of this thing. Then I have my omega dot times rho xyz is 0. Then finally I have omega times rho xyz. My omega is equal to 10k times, I write it omega times rho, and that's equal to 10k, and that becomes 10k. And my rho at this instance is also equal to 1k. Again, this produces 0. So now I have all of the term that I needed for my acceleration. My r double dot o, I have it. My axyz, I have it. And 2 omega times vxyz is plus 100i. And I do not have any other term. So you can put them together, and you can say acceleration point P respect to main reference frame is equal to minus 500 plus 100i. And minus 500 plus 200, that becomes minus 300j. Plus minus 35k feet per second square. Any question on this problem? Relatively straightforward problem. There is not that much ambiguity what you should do in terms of the auxiliary. Let's solve another problem. So if you see the astronaut, we used to have a professor here who was astronaut. He went with the shuttle to the orbit, and he spent maybe some time in the orbit in the laboratory. And he was a professor in chemical engineering, but he left. And right now he's a dean of one of the university in Texas. And when you see this guy, he had a big neck, huge neck, huge neck. He has this much neck. He had this. Why do you think he had that much neck? His neck was huge. Why do you think that he had that much neck? Huh? What's that?
Radiation.
Radiation? No, no. Nothing to do with radiation. Come on. He was a huge neck. Huge. Almost 2 times of mine. Mine is miniature neck. His neck was very big. Yes?
I'm guessing he was a pilot before he was an astronaut?
Well, he has to go through some exercise. They put on different kind of inertia, different movement, and as a result, he developed big muscle. In order to carry those big inertia, that's during the lift up, otherwise your bones get crushed. During the lift up, or you could have a huge 10 times of your weight. Just think about it, you put your 10 times your head and your neck. You have to have a huge bone, huge muscle to hold it because of that inertia. And we'll talk when we go to dynamic problem. Maybe I bring the head of the astronaut and I ask you what kind of forces happening to the neck of this astronaut as a result of all of this motion that's happening. And with acceleration, all of those inertia that it has, how much neck is happening. It's like that when you are going up in the elevator, you think that there's some extra force is against your feet. Have you experienced that? When it goes up, then you feel that much more force rather than your weight alone. When it is coming down, then you see something is rugging the pool under your feet. You don't see any reaction. So almost you are as if you are flowing. So when the system is going up with such a huge inertia, you develop huge force against your body. So that is your bone can get crushed. When it is coming down, then with some inertia, then as if you are putting no forces almost there. So we talk about that, or some other forces. So that's the reason this astronaut, they have to go on the training for 6 months, 7 months, and so forth, and to make sure that they can tolerate all of those maneuver, because all of those inertia, and see what kind of problem they develop. And as a result of those exercise, they develop huge muscle in order to be able to carry those forces. But anyway, so this is a reason that those astronauts that they have a huge neck. So this is our next problem. And you're going to have some homework problem that you have to use this auxiliary coordinate system to do the work. So let's say that we have a training astronaut, and this is my astronaut is sitting on a chair. My astronaut is in this cabin, and there is a chair here. There is a right now chair here. And this astronaut is sitting, and this is the head of the astronaut. This is the head of the astronaut, which is 3 feet from the chair. 3 feet from the chair. And this astronaut is twisting here inside of this chair with angular velocity of 7 feet per second. 7 radian per second. So it is rotating with omega dot, and omega is the angle, radian per second. As if like this. This is my head of the astronaut, and this is going around like this. So you do have something attached to his chair, and the chair is rotating. So you can think about it like a chair, and the chair is rotating inside of this. So the box itself the box itself is being twisted in this direction with 20 radian per second. So this is the box. The box is rotating like this. The box is rotating around this axis. The astronaut inside the box is rotating inside the box in the different directions. So this is rotating in this direction. So the astronaut is going in this direction, something like that. So two different direction of rotation. So one rotation is here, one rotation here. So you can think about it that you do have a disk here, and this disk is going like this, is rotating like that. And inside the box, it's going in this direction. So two different rotations. So one is rotating here, one is rotating here. So two different rotations. I hope you understand. And the distance of this one to this location from here to the center of the here is 10 feet. And now you have another mechanism here, another arm here, which is at the distance of 30 feet. The whole system is rotating around this axis with 10 radian per second and 5 radian per second square. And this is your capital Y, this is your capital Z, and that's your capital X. And this is going with the 20 radian per second. So you do have the whole system, you do have a lot of rotation. You do have a lot of rotation. Just think about it that you do have something going like this, perpendicular to the blackboard. The whole blackboard is going like this, and then the whole room, it goes like that. Very crazy. So something going like this, then it goes like that, then the whole thing goes like that. Very crazy. That's the reason that astronaut is subject to a lot of forces. All right? So now we are interested to see what kind of acceleration and what kind of velocity, because when you write the Newton's law, you have to write respect to the ground, respect to fixed reference frame. The question is that what is the head of the astronaut is feeling in terms of acceleration? And that acceleration is produce a lot of force. F is equal to ma, and that is reason that astronauts should be able, their neck has to be able to tolerate that force. So they put them in this kind of devices, simulator, and they put all kind of motion. And if they throw up, they say next person. And if they throw up, the next person, until they find somebody that they can tolerate forces as well as he doesn't throw up. So we are not talking about throw up part of it, because that would be extra degree of freedom. So something is coming up, then we have to talk about those things as well. So we are not talking about that part. So we have enough complication in our life right now. So now we are interested, respect to main reference frame, what is the head of the astronaut is feeling. So how should we do that? A lot of different motion, and we are interested what is the acceleration head of the astronaut. So we attach some auxiliary reference frame, maybe right here. We can call it a small x, y, z. A small x, y, z. And maybe we can call it x1, y1, z1. And where is this small x1, y1, z1 is attached to? Where is this small x1, y1, z1 is attached to? Huh? Attached to what? You have to make sure what is attached to what. Huh? Attached to astronaut? That's what you would like to say is attached to astronaut? Okay. Yes. Attached to the box. Or attached to this shaft. That chair is sitting here is this one. And it is basically this one. Forget about astronaut. This is basically attached to this cabin. Attached to the cabin. That's all we have to say. It's attached to the cabin. It's not attached to astronaut. It's attached to the cabin. It's like that. This one is rotating like this. Forget about what's happening inside. That astronaut is doing like this. Forget about that part. This is attached to the cabin. Very important to understand where it is attached. Where it is attached. Because otherwise you get it. So that's one auxiliary reference frame. Let's attach another auxiliary reference frame right here to this one. To this one, which is attached to this arm, to this one. Let's call this one X2, Y2, Z2. And then we do have our main reference frame. So you do have 3 reference frame here. 3 auxiliary, or 2 auxiliary and 1 reference. Okay. Again, you have to understand where the things are attached. Where the things are attached. Okay. Now you implement those equations that we had. Velocity at the point P respect to main reference frame. This is generic equation is R dot O plus Vxyz plus omega times rho xyz. This is our generic equation. You apply this equation one at a time. From this you go to this, and then from this you go to this, and then you are all set. All right? And then we find velocity. So let's do one at a time, then you will understand what I'm talking about. But that's a generic equation. So now you have to say velocity of the head of the astronaut, let's say P, respect to velocity of point P, respect to a small x1, y1, z1. What is that? So you can say that, okay, so let me just do this one. So you can say, forget about here, and that is what is an astronaut is rotating respect to this axis. His head is here, 3 feet from here, 3 feet from here, and my auxiliary reference frame is attached here. Auxiliary reference frame is attached here to this point, and the disk is going around that location. Around that thing is rotating. So you have to say we are interested velocity respect to x1, y1, z1. And your generic equation is R dot O plus Vxyz plus omega times rho xyz. That's your generic equation. That's your generic equation. So what is, and of course this one I'm talking, we go from the, let's call this one x2, y2, z2. So we go directly to that point, because we are going from this coordinate to this coordinate. That's basically we are talking about x2, y2, z2. So from one coordinate you go to another coordinate, and then from another coordinate you go to the last coordinate. you could have 10 different coordinates. You start from the last one, then you go to the next one, then you go to the next one, then you go until you get to the ground. All right. So let's go ahead from here. What is the velocity of this coordinate respect to this coordinate? The point O. Forget about astronaut. Forget about astronaut. What is the velocity of the x1, y1, z1 auxiliary coordinate system respect to x2, y2, z2? What is that velocity? Can somebody tell me what's that velocity? Forget about astronaut. Yes?
0.
0. Do you agree with him? Do you agree with him? You are shaking your head. You are shaking your head. You disagree with him?
Yes.
You agree with him? Okay. I'm glad you agree with him. So just forget about astronaut. There is no astronaut here. This is the coordinate of the box. The box is going like this, all respect to this coordinate system, and this point doesn't go anywhere. This point doesn't go anywhere. My auxiliary reference frame, this one respect to this coordinate system, doesn't go anywhere. It rotates. It rotates. Certainly it rotates, but it doesn't go anywhere. It doesn't go anywhere. It is still attached. It's like that. This is my shaft here. This is my box. Forget about astronaut that is inside the box. And this is going like this, like that. This point doesn't go anywhere. That's my box. This is the box that astronaut is inside of this box. Astronaut doesn't do anything. And this is rotating like this. The box is rotating. So the point O of the box doesn't go anywhere respect to here. So that's 0. Now you have to say what's the velocity of the x, y, z respect to this coordinate system, respect to this x1, y1, z1. We better say x1, y1, z1. Well, this is my astronaut, and his head is here, is going in this direction, and that's r omega. And at this instance, r omega is in this direction, and that is bingo. And that's equal to 3 feet times 7, that's 21 feet per second. And at this instance is in the direction of capital J, negative capital J. So this one is minus 21 capital J. No problem. So as if this is your main reference frame, this is your auxiliary. Then you do have this term, omega. And this is my auxiliary reference frame is being twisted times rho xyz and rho respect to xyz that you have auxiliary coordinate system. So this is your main reference frame as if this is main, and this is your auxiliary. So as if this point is fixed, forget about this one. Just this coordinate system respect to this coordinate system. This coordinate system is being twisted by this omega, and rho xyz is here, rho xyz. So that's equal to 20j, and rho xyz is equal to 3 feet k. And this becomes j times k is equal to I. So that becomes 60I at this instant. So that becomes 60I. So let's recast it again to make sure you understand what I'm talking about. In this case, I have 2 auxiliary and 1 main. This is 1 auxiliary right here attached to here, and it is attached to the cabin. There is another auxiliary which is attached to this one, And then I have the main. So I have 2 auxiliary and 1 main. So you will just say, forget about this one. as if this is my main reference frame. So now we have to say, okay, what is the velocity of this point respect to here? Forget about other rotation. Forget about other rotation. This is simply rotating 20 radian per second. So this small auxiliary is doing like this. It's doing like this. Forget about other rotation. There is no such thing, other rotation. We don't have any other rotation. We just have this one, and this rotation make this auxiliary rotate. Okay? So that's one thing that you have to understand. Now you will go to implement. You say, what's the velocity of this point respect to here? Well, this doesn't go anywhere. The cabin stays in its position and rotate around here. This position doesn't go. So r dot O is equal to 0. No, just forget about this rotation. Forget about all of this thing. And this guy is sitting here, and he's going like this. Well, you can say is r theta dot, and is in that direction. So that's negative j. So r theta dot, r is 3 feet, theta dot is 7, so that becomes minus 21j. Finally, now because this auxiliary reference frame is twisted respect to this one, then you do have another term, omega times rho xyz. And omega, which is this auxiliary reference frame, is being turned, is attached to the cabin. And this is rotating with 20 radian per second. And rho is equal to rho respect to its own coordinate system is 3 feet. So you put it back here. So that becomes 20j times rho. Rho is equal to 3k. And j times k is I. That becomes 60i. So now you go from this coordinate to this coordinate, as if the rest pretty much doesn't exist. So now you can say, OK, again, implement this equation. Velocity of the point P respect to main reference frame is equal to r dot O plus v respect to x2, y2, z2 plus omega, that my auxiliary reference frame is being twisted, time rho respect to x2, y2, z2. So now this time, forget about this coordinate. This is your auxiliary, and that's it. That's your equation. So you go from the x1, y1, z2 to x2, y2, z2. Then you go from x2, y2, z2 to capital X, y, z. Now let's implement this equation. So what is r dot O? What's r dot O? Forget about all of this attachment. What is the velocity of this point respect to this x, y, z? What's that? Would be how much? R omega. And r is how much? 30 feet. Omega? 10. 300. The direction? Capital I. The direction capital I. So that would be 300 capital I. So this is going around the circle. Forget about all of this attachment. This is my coordinate system auxiliary, and this is going like this around the circle. And that circle at this instant is coming toward the I. That's r omega. R is 30, omega is 10, 300 I. No problem. Velocity with respect to x2, y2, z2, I already found it. Is minus 21j plus 60i. So I already have that one. So minus 21j plus 60i. I already have it. Now you have to say omega time, and omega, which is my auxiliary reference frame, is being twisted. This is my auxiliary reference frame. This time, this is my auxiliary reference frame, is being twisted respect to here. So you have to say omega times rho xyz, and omega is equal to 10k times rho xyz, rho respect to x2, y2, z2, and rho respect to x2, y2, z2 is 10 feet and 3 feet. So that would be minus 10j plus 3k. And if you multiply these things, so this is the last term. So this one plus this one that we already have, and then this is the last one. So if you do that, velocity of point P respect to main reference frame is going to be 300I minus 21J plus 60I, and K times J is also I. K times J is negative I. That becomes 100I. So altogether, you get 400I minus 21J plus 60I. So that would be, that would be 460I minus 21J. So velocity at the point P, respect to main reference frame, is 460I minus 21J feet per second. Let me just check with my notes to make sure this is correct. That's correct. So let's recast it again. Sometimes the problem is very complex. And of course, I haven't done acceleration. Maybe I do acceleration next time for you. Or maybe I just do it. We have still 10 minutes. Maybe we can do the acceleration. So this problem is a little bit complex. The astronaut is going like this. The cabin is going like this. The whole thing is going like that. This is what the hell is going on. It would be very difficult to analyze in one shot. We have to have auxiliary. More auxiliary, better you are. But you have to know what's going on. So we attach this auxiliary to the cabin. What is happening inside the cabin? I don't care. It is attached to the cabin. Astronaut is walking inside the cabin. Astronaut is sleeping inside the cabin. I don't care. This is attached to the cabin. And another auxiliary reference is attached to this piece of metal, which is being twisted. So now, and then I have my main reference frame. So now you go ahead and say, what's my generic equation? My generic equation is R dot O respect to another coordinate system, x2, y2, z2, R dot O. That's a generic plus V x1, y1, z1 plus omega times rho x1, y1, z1. That's your generic equation. That's your generic equation. So you are going from this auxiliary as if this is your auxiliary and this is your main. Forget about the rest. Forget about the rest. So what is the velocity of this point? As if this is rotating like this, you should say it never goes anywhere. It never. For this configuration, if this is my auxiliary and this is my main, respect to here doesn't go anywhere. So that's 0. You put 0. Then you can say, OK, now forget about this rotation. My astronaut is going like this, going all around like that. So that velocity is r omega, 3 times 7. And the velocity in that direction is equal, at this instance, is negative j, minus 21j. Now you said this cabin is being twisted. Twisted. And as a matter of fact, when it is twisted, the head of the astronaut is coming toward the room. And you should say right away is omega times this angle, so 60. So you should say right away the head of the astronaut is coming like this, is rotating like this, it's coming out. So you can say omega times that, and omega is equal to 20 capital J times rho 3k. The answer becomes 60I. So velocity of the astronaut head respect to the x2, y2, z2 is minus 21j plus 60I. Now you go from this auxiliary to this main. Forget about the other auxiliary. So again, you apply your generic equation. What is the velocity of this point? As if the rest doesn't exist. You said no problem. If the rest doesn't exist, this point goes around the circle like this, r theta dot, and r is 30, and theta dot is 20, so that becomes 300, and the direction of that one is coming toward the room. That should be in the direction of x direction, should be 300I. Then you do have v x2, y2, z2. We already have that velocity from the previous one. That is minus 21j plus 60I. So we have that one. We don't have to calculate again. Then you do have omega, that your auxiliary reference frame is being twisted. This time this is the omega for this. This is my auxiliary, and this is my. How is this one is being twisted? Well, this one is being twisted because of this. Is attached to that point. Is attached to that point, and therefore it goes around with that. So you can say that it has omega is equal to 10k times rho respect to x2, y2, z2. Rho respect to this auxiliary, and that's a rho. That's a rho this time. And the rho is equal to minus 300j, minus 10j, plus 3k. You put them together, and that becomes velocity. That becomes 460I minus 21j. All right, now we would like to find acceleration. Again, you apply your generic equation. Of course, it has more term on your generic equation, but let's write that generic equation. Acceleration of point P respect to the x2, y2, z2 is equal to r double dot O respect to x2, y2, z2 plus acceleration of P respect to x1, y1, z1 plus 2 omega times v x1, y1, z1 plus omega dot times rho x1, y1, z1 plus omega times rho x1, y1, z1. So that's your generic equation. So again, forget about this rest of the structure. Forget about astronaut. What is r double dot O? What is this? What is this term? Forget about astronaut. Forget about the big attachment. As if this is a coordinate system, and this cabin is being twisted like, what's the acceleration of this position? What's that?
0.
0 again. It doesn't go anywhere. That's 0. That's right. That's 0. That's correct. It doesn't go anywhere. So that should be 0. You have to think about it, what's going on. It's not easy. No, you just forget about all of the things that's going on, and you can say that my astronaut is here, and my astronaut is being twisted. It goes around here with a 7 radian per second, and this is the head of the astronaut. What is the acceleration of this position respect to the x1, y1, z1? What's the acceleration? What's that? R omega squared. In which direction? Negative k. Negative k. R omega squared. You all understand that. So that is 1 feet, 3 feet. Omega is 7 squared. The direction of that one is a k, negative k. So that is your A, P, respect. Forget about the rest. All right? Forget about the rest. That is a small one. Now you do have 2 omega times Vxyz. 2 omega times. What is this omega? What is this omega? What is this omega? Omega, that auxiliary reference frame is being twisted. That is omega, that auxiliary reference frame is being twisted. So that auxiliary reference frame is being twisted by this one. So that is 2 times 20j, and velocity with respect to x1, y1, z1, we already had that one. is minus 21j. We already had that one from previous calculation. Velocity with respect to x1, y1, z1 is minus 21j. Minus 21j. And of course, this term would be 0. This term would be j times j is 0. Then we do have omega dot times rho x1, y1, z. Well, this is going with the constant. Again, we don't have this term, so that's going to be 0. For this problem, it's going to be 0. Because we are not talking about it with respect to main reference frame. This is the omega of auxiliary reference frame. Not omega of astronaut. Has nothing to do with that. This omega in this equation is auxiliary reference frame rotation. Finally, we have omega times rho xyz. And again, this omega is 21j. 20j times 20j and times 3k. So your acceleration of point P respect to x2, y2, z2, you just simply write this one. Acceleration of P respect to x2, y2, z2 is equal to minus 49 times 3, that becomes 147, k, j times j, forget about it, and then I have 400 times 3, that becomes 1200. 1200. J times k is equal to I. J times a, I is equal to negative k. So that's negative k. Yes. Huh? What's that?
Then like 2 times omega times vxy, vxi, y1, x1, y1.
This one?
Yeah.
That's j times j.
Yeah.
J times j is 0.
The later one,
Huh?
I think it's like 2400k.
Huh? What?
2400k.
2400k? Which one? I don't understand.
Never mind. No, sorry.
You sure? According to my note, this becomes minus 1347k. So this is acceleration of point P respect to x, x2, y2, z2. Now we have to go from this to this. Why don't we stop here and we do it next time? Go through the velocity, make sure you understand the velocity part, and because we are going to have, you are going to have this kind, and then we solve some more problem.